right, so here we go. We have a really good understanding of what happens if we have an ideal gas. We've talked about ideal gases. We've talked about the behavior, the sort of 4 important postulates for ideal gases. What we need to think about going forward, what we need to think about now, is really sort of thinking about how we can, the last little piece of this, how we can compare real behavior or situations where a gas might behave in a non-ideal fashion. Okay? If you recall, there were 4 important postulates. Okay? Gases move in continuous straight lines. It's the collisions of the gas particles with the hits with the container walls that cause pressure. We talked about the volume of the particles. We said that a gas particle takes up a very small volume compared to the total volume of the container. In fact, we assumed that the volume of the particles was so small compared to the whole container that we could consider it to be 0. Now, atoms and molecules obviously have a non-zero volume. They take up some tiny amount of space. So if we really wanted to more accurately model this, we'd need to take the total volume of the container and subtract out whatever volume the particles themselves are already taking up. So we can improve the ideal gas law. We can make it more accurate by going ahead and saying, hey, if this V is the total volume of the container, then the volume that each individual gas particle could be in is going to be the total volume of the container minus the number of gas particles, moles, times what volume each individual particle occupies. So the B factor here is essentially the volume per mole of particles. What volume do the actual molecules take up? So this is some value that we'd have to go through and measure or calculate for each individual or for each different type of molecule. Carbon dioxide would have one, hydrogen would have a different one, nitrogen would have a different one. We'd have to calculate that value or look it up in a table. In fact, there are tables in our book that list these B values, the molar volume of the particles.
For ideal gases, don't they all take up the same amount of volume?
That was our assumption, right? But we're talking about now what we call real gases, gases that might not be following the ideal gas law. This will happen a lot when we have high pressures and low temperatures. If the gas particles are at low temperatures and high pressures, and low temperatures are, tens to hundreds of degrees Kelvins, okay, that's a low temperature. If the pressures, we're talking, hundreds, tens to hundreds of atmospheres. Those are high pressures, okay? Those are situations where the ideal gas law doesn't work very well because the volumes tend to be small, so the importance of the particles is larger. Additionally, we also talked about, remember, we talked about the particles moving around and not interacting with each other. There's no attractive or repulsive forces. That is, that the particles are free. When they hit each other, they bounce off in an inelastic collision, okay, where they hit and they bounce off. And then we don't have to worry about attractive forces between the particles. Now, again, we know that can't be really, really true. The particles we've been talking about are, for instance, water vapor is highly polar. When 2 water vapor molecules are going to come next to each other, they're going to bend. There's going to be an attractive force. So in our ideal gas law, they hit and they bounce off. They hit and they bounce off. In the real world, right, in the real gas, they hit and they're attracted to each other. So they might change their direction. They're going to be attracted more towards each other than, say, the outside walls of the container. So the pressures that we measure, is actually lower than the sort of idealized pressure would be. If we want to calculate this, we have to add back in a factor that takes into account how much are the gas particles being attracted towards the middle of the container. And again, the idea here is that if these gas particles are attracting each other and they're not attracted to the walls, that attractive force It pulls them in towards the middle, okay, and makes the pressure, the measured pressure, lower than it should be. So we have to add in a corrective factor for that pressure. Now the corrective factor depends on the number of particles and the volume available to those particles, and some factor A, which measures the attractive forces between the particles. The greater the attractive forces, the greater this A value will be. Okay, the bigger the A value, the greater the attractive force. The greater the B value, the larger the volume the particles occupy. So A takes care of our attractive force inconsistency, and B takes care of our volume of the particle inconsistency. We can now substitute this term in for our volume and this term in for our pressure. And so we have this new equation, which is called the van der Waals equation. Okay? The van der Waals equation is an equation that we could use to deal with real gases. So, remember our PV equals nRT? Well, here we have, this is our corrected pressure, and this is our corrected volume. Okay, V and P are the measured values. These are the actual measured values. These, the whole term here, would represent the corrected pressure and the corrected volume. And all we need to do is look up those A and B values, and then we can plug in and solve just like we've done all the other gas law stuff. We have to find / measure the attractive force, or if for our purposes, look it up on the table. Yeah.
So this is a real P and the real.
Now, this P right here is the measured value, just like before. And this V right here is the measured value, just like before. But this whole term would be the sort of real pressure. Yeah. Well, yeah. Yes, the calculated value, let's call it that. Question? Yeah, they'll give you the A and B values if they ask you to do any calculations of this. That's pretty unlikely. They don't typically ask you to do calculations. The most I've ever seen with this really is in some multiple choice problems where they ask you to, in the van der Waals equation, the variable A represents the 2's from the 5 things. And so you would say, oh, it represents the attractive force between the particles, not the one that says the volume of the particles, because that's B. Okay, but we're going to do a calculation just so you can see what it looks like. So it turns out that the number of attractive forces, that the importance of this term depends on the particle density. The more particles there are in a given volume, the greater and more important this factor becomes. They're both squared. This is an empirically derived law. So what happened was somebody collected a bunch of data and came up with an equation that mapped onto that data. I'm not 100% sure for a theoretical reason why we'd have to look that up. So yeah, we could look it up. I'm sure if we Google the van der Waals equation, I'll look it up and we can go over it. I know it has to do with the particle density. Why is it squared? I don't remember. B is going to have units of liters per mole, and A is going to have units of moles squared times atmospheres over liters squared.
Moles squared times atmospheres.
Yeah. You think if we're adding it to pressure, it has to come out to be units of atmospheres.
So B is liters over.
B is going to be whatever we need to get to liters, so that's going to be liters over moles. And then A is going to be moles squared times atmospheres over liters squared. Moles squared times atmospheres, times pressure in atmospheres, divided by liters squared. Those units are typically given to you in the problem. They're functionally irrelevant because the units of A are whatever units it needs to make this work, so that we can add pressures together, so add atmospheres. right? So I'm telling you what those units are, but they're just the units that this variable has. And this is essentially just a fudge factor. It's a measured value that makes this equation come out and work. Okay?
Would it be possible to isolate, if you have every other value, to isolate B, like if we didn't know volumes per mole of
Yeah, you can measure, these are measured values by and large. A and B are measured values. Like you conduct, hey guys, you conduct experiments measuring pressure, temperature, moles, and volume. You measure it all. And then you say, hey, my ideal gas law predicts this line. My experimental data is giving me this line. What values of A and B make my experimental data match the ideal gas law? That's how they calculate them. So the way we do it, literally the way those values are generated is exactly what I said, is you collect a whole bunch of pressure, temperature, volume, and mole data for a gas. Like you measure it under a bunch of different conditions. You would basically graph that data, compare it to the ideal gas law, and then solve for what variables, what numbers for A and B make this equation match the ideal gas law. Right, we have the equation. No, what we get the A and the B value. We plot the data, right? And we can generate an equation for that will describe that if you want to plot that data, right? Because we just collect the data by measuring temperature, volume, pressure, and moles. And then we collect that data and we look at the two graphs. And then we do a mathematical trick to say, hey, how can I make this data fit this equation? What values of A and B make it work? And then we solve for A and B in that way. It's just all experimental measurements. We can just look it up in the table because people have already done all those measurements. And that's, by and large, beyond the scope of the class. It's not something that's going to be on the test. Okay? So, it's interesting, and let's double check why those are squared. I remember someplace a mathematical treatise that showed why, but it may be even in our book. I have to double check. What we functionally need to be able to do is say, what is A and what is B? What do they represent? And perhaps be able to solve a problem like this. So our rocket, 10-liter pressure chamber of the rocket is loaded with 1.93 moles of carbon dioxide at 50 degrees Celsius. Calculate the pressure. So we can do that with the ideal gas law, right? So use the ideal gas law to calculate the pressure. Yeah, it's got to be in liters or else you're going to change your R value. And the key is that the R value that we always use, 0.0821, is in atmosphere liters per mole Kelvin. That sets all the units. If you change the units, then your R, the physical value of the R is different. All right, solve for it. Do the ideal gas law. PV equals nRT. I gave you 3. Solve for the 4th. All right, do we got this? So pressure is equal to moles times R times T divided by volume. 5.12 atmospheres. Okay, ideal gas law says 5.12 atmospheres. Now, here's your A and B value. What pressure would we really measure? I'm going to let you, it's going to take a little while. You know the ideal gas law equation, right? I gave it to you. You have all the variables but P. You need to substitute and solve for P. It's more complicated math. There's addition in there, there's squares, there's lots of more variables. We just solved for P using the ideal gas law. I want you to solve for P using the van der Waals equation. A and B are given in the problem. So use the van der Waals equation and solve for P. All right. Here's our van der Waals equation, right? Should start with this. We know N, we know V, we know A, we know V, we know N, we know B, we know N, R, and T. Substitute in for all those things, right? We're going to substitute in for all those bits. 1.93 squared, 3.59, 10. 10 minus 1.93 times 0.0427, 9.3, blah, blah, blah. What did I leave off here? There's something I left off. I forgot. Times. Yeah, you got to have the temperature in Kelvin there. Now, did I do, I think I actually did it. I didn't put it on there, yeah. See here? There's a multiplication sign missing.
Mr. Fleming, is the NRT the same as in the first equation?
Yeah. So we simplify all the numbers down, right? I did this, subtraction gave me this. I did this math, it gave me that value. I did all this math, it came out to 0.1337. How cool is that? That's crazy. I didn't even notice that before. It's 1337. It's not bad. It's funny. It's leet. Somebody ask somebody to explain it to you. Not important. It's funny. Because it's leet. It's okay, you won't ever understand. You're not enough of a computer geek. Then this will never be good for you. All right, so we divided the 9.918 to the other side. We're going to subtract out the leetness from that number. So if you were a computer user in the 70s and 80s, you would have spent a lot of time on the proto-internet bulletin board systems, where you would communicate, if you were cool, using a mixture of numbers, symbols, and letters to write, because it was fun. And it carried over into, modern day in the 90s and stuff. Computer hackers would use it. Also, you would see it on things like pagers. So if you're using numbers to talk, leet means like elite. Comes from the word elite. So if you're elite, that means you're elite. You've got mad skills. Anyway, this is why, if you notice my tracksuit, the faculty tracksuits we got, the back of mine, 1337. So pressure 5.03 or thereabouts, depending on your rounding. Did you get it? All right, looks like our rocket is good to go. I'm pretty sure that's a model.